Hi everyone, welcome to Learn and Code. In the last session, we have written the program for implementation of relational operators. So before going to see other programs to implement logical operators and bitwise operators, let us have a discussion on bitwise operators. Let us go to bitwise operators. So bitwise operators can be divided into first one, we write it as bitwise and. So next we are using the pipe symbol. This is known as bitwise OR, and another one is bitwise exclusive or we write as XOR. Next, bitwise complement, bitwise left shift, and another one is bitwise right shift. So these are the operators which are used at bit level. So what is the main purpose of these bitwise operators? So bitwise operators work at low level. So when the operations are performed on bits, so that we can increase the execution speed. The main use of bitwise operators is to increase the execution speed. So we will discuss one by one. So how to use bitwise AND operator, bitwise OR, and bitwise exclusive OR, and bitwise complement, or we write it as one's complement. After that, bitwise left shift and bitwise right shift. So we will discuss with examples. Now I'm going to talk about bitwise AND. So before moving to bitwise AND, you should know the concept of binary number system. Binary number system. So we know that the binary number system is denoted as like this. We are writing zeros and ones, and the base we are taking is 2. This is the representation of binary number system. For example, I have given a number like this 5. So generally we write the numbers in decimal number system. So this is decimal number system. So how to represent this decimal number system in binary? So what you have to do, we have to convert this 5 into the decimal number into binary. So how to convert? To convert into binary, you divide 5 with 2, and we know 2 2 ja 4, the remainder is 1. 2 1 ja 2, the remainder is 0. Now in this case, 1 is not divisible, but you can write 200, and here you can write 1. So the decimal number 5, generally the base is 10, but no need to write 10. So 5 is denoted as 101 and the base 2. So this is the way of converting the decimal number system into binary. Okay. Now why I'm talking about this number system? Why? Because before using bitwise AND, you should know these basic concepts to how to convert the decimal number system into binary and binary number system into decimal. So this is the conversion from decimal number into binary. Now how to convert this binary number system into decimal? That also we will see. Now take 101. So here I'm taking left side. The number in binary is 101. After taking these bits, now you start from right to left. You write 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. So now 2 to the power of 0 is 1, then 2 to the power of 0 into 1 plus 2 to the power of 1 into 0 plus 2 to the power of 2 into 1. This means 1 into 1, 1 plus 2 to the power of 1 is 2 into 0, 0 plus 4 into 1, 4. So here we are getting 5. So this is the decimal number 5. So this is the way of converting the decimal number into binary and binary to decimal. Now we will give an example to use bitwise AND. Now what you do is you take a number, for example, a equals to, I'm taking 11, and b equals to Assume that I'm taking the number 10. These are the two numbers. Now, when you perform bitwise AND between A and B, bitwise AND is also called binary operator. Now, what do you do when you write A and B? For example, I'm giving like this: C equals to A and B. So now, the meaning of this is 1, 1, 1, 0 AND operation, and here we are going to get the result. So, what we are going to get in C? What is the result of C? That we will see. Now, to perform this operation, first what you do is take a number 11 and convert into binary. So, what is the value now? 2 5 is 10, the remainder is 1. 2 2 is 4, the remainder is 1. 2 1 is 2, the remainder is 0. 2 0 is 0, here we are taking this 1 here. Now, its equivalent value is 1011 base 2. 1011 is the binary equivalent of 11. Now, what is 10? Again, take 10, same concept. 2 5 is 10, the remainder is 0. 2 2 is 4, the remainder is 1. 2 1 is 2, the remainder is 0. Here you write 0 and 1. So here 10 is nothing but 1010. You write from bottom to up 1010 and the base is 2. So now, so A and B, that means 11 and 10 is nothing but 11 is 1011 and 10 is 1010. Now you apply the operation AND. The operator bitwise AND operates only at bits. Even though if you give the decimal values like 11, 10, those are internally converted into bits, and I'm writing like this: 1011, 1010. Now we have taken the example. Example is 11, 10, right? AND operator. So we have written that 11 is represented as 11 is the decimal number, and it is converted into 1011, and 10 is 1010. So here we are applying bitwise AND. 100, 111, 00 is 0, 11 is 1. So we are getting 1010. So decimal value, it is the binary value. Its corresponding decimal value is 10. So if you perform bitwise AND operation between 11 and 10, it gives 1010. So we have taken the example. The example we have given is 11 and 10. So 11 is converted into 1011 and 10 is converted into 1010. Now you apply bitwise AND 10. So simply you can write the product 1 into 0, 0, 1 into 1, 1, 0 into 0, 0, 1 into 1, 1. So we are getting 1010 base 2. So the equivalent decimal number is 10. The answer we are getting is 10. Okay, by performing the operation C equals to A and B, now we are getting C value as 10 in decimal. So this is the way of using bitwise AND. Similarly, if you perform bitwise OR operation, C equals to A or B, so what we are going to get, same logic, 1011, 1010. But here we are using bitwise OR operation. So it is like a plus operation, 101, 11 also 1, and 0 is 0 plus 0 is 0, 1 plus 1 again 1. We are getting 1011. So in this case, we are getting the value 11. This is bitwise OR operation. C equals to how much? We are going to get 11 when you perform bitwise OR operation, and C equals to 10 when you perform bitwise AND operation. So this is about bitwise AND and bitwise OR. Now after completing this, we are going to use the operator bitwise NOT. Bitwise NOT. So bitwise NOT is nothing but if it is 0, we're getting 1. If it is 1, we're getting 0. But instead of saying bitwise not, there is no bitwise not operation. Just we are talking about bitwise and bitwise or and bitwise exclusive or. What is bitwise exclusive or? So for the same example, C equals to A and exclusive or B, I said A is nothing but 11, B is nothing but 10. Now we are performing bitwise exclusive or operation. Exclusive or in this case, what you do is 11 is 1011 and 10 is 1010. So while performing exclusive OR operation, what you do is it is similar to OR operation, but the thing is 1 1 becomes 0. 1 0 1 1 1 becomes 0. 0 is 0 is 0. 1 1 is again 0. So in this case, we are going to get that decimal value 1. So by performing C equals to A exclusive OR B operation, we are getting the decimal number 1. So this is about bitwise exclusive OR. After bitwise exclusive OR, we are moving to next operation, bitwise left shift. We call it as bitwise left shift. So before moving to bitwise left shift, very important thing is whenever we have taken the variables like A or B and we said that A equals to 11 and B equals to 10 and we said that C equals to, we are performing operation like A and B. Another one we have said that A or B, and we have taken that another example C equals to A exclusive or B. So in this case, what you do is, so whenever we take three variables and each and every variable takes minimum 1 byte. 1 byte means 8 bits. So I said that A equals to 11, 11 in the sense 1011. Its binary equivalent is 1011. B equals to 10, its binary equivalent is 10102. So actually, though there are 4 bits, it is represented in the form of 8 bits. It is represented in the form of 8 bits. So here 1, 0, 1, 1. These are the rightmost 4 bits. The remaining 4 bits are filled with zeros. That means 1011 is represented as 00001011. It is represented internally like this. Similarly, 1010 is represented as 0000 and 1010. After converting into this 8 bits, then only it is going to perform the corresponding operation and it gives the result. So this is the bit level operations. Now we will see left shift operator. Left shift. Now how to perform this left shift operation? We have taken A equals to 11. Now we are saying that C equals to A left shift 2. So here 2 indicates the amount of shift. The amount of shift. Now you do one thing. A is represented as how many bits? Just now I said that 8 bits. 0, 0, 0, 0, 4 bits. And last 4 bits are 1, 0, 1, 1. These are 4 bits, right? This is A. Now we are shifting how many bits? 2 bits left. We are shifting the left to 2 bits left. So when you shift these 2 bits, what happens? We are getting the internal storage like this. So 0, 0, 1, 0, 1, 1. And right side we are getting 2 empty spaces. These empty spaces are filled with zeros. Now, if you convert this binary into decimal, now what you are going to get is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5. So in this case, what we are going to get is 32 plus 8 plus 4. That means we are getting 44. 44 is the decimal value. So when you perform left shift operation, the amount of shift is 2. 2 bits we are shifting left. So left side 2 bits are removed and right side empty places are filled with 2 zeros, and the result we got is 44. So the same 44 can be given by using the principle. So what is the value? A value 11. So to get the final value, we write it as 11 into the amount of shift we have 2 to the power of 2. 11 into how many bits we are shifting? 2 bits. So you take the 2 to the power of the number of bits shifted, that is 4. Total how much? 44. So to get the result, to check the result, what you do is take the given number 11 and into, you find out the 2 to the power of number of bits that are shifted. So we are getting 44. This is the way of performing left shift. Similarly, we are talking about right shift, bitwise right shift. In the bitwise right shift also we are doing the same concept. Now, for example, I'm writing C equals to B right shift 2. Any number of bits you can shift. B right shift 2. Now, B value, what I said, 1 0. Right shift 2. 1 0 means you know already it is represented as 1 0 1 0. So left side bits are 0 0 0 another 0. Now we are using right shift, means these bits are shifted right. So these 1 0 gone and we are getting like this 0 0 0 0 and 1 0. Left side again empty places are filled with 2 zeros. Now what we are going to get? We are going to get the result 2. The number we are getting 2. Now how to check the answer like for this? So like previous example, take the number b value 10 into, previously we have multiplied, but here you divide by 2 to the power of how many bits are shifted? 2. 2 to the power of 2. Previously we have given 11 into 2 to the power of 3, but here 2 to the power of 2, but here you take 10 by 2 to the power of 2. That means 10 by 4. 10 by 4 means how much you are going to get? 4 2 is 8. 2.5. But don't take the fractional part, you take only 2. So here we are getting the answer 2. So while going for the division, you take only the integer part for the right shift. This is the way of checking your final answer for the left shift as well as right shift. For the left shift, you multiply. For the right shift, you divide. So this is about the right shift operation. Now after performing, now we'll see bitwise complement. Bitwise complement, or we write ones complement. For example, just now we have taken that C equals to, so bitwise complement of A. That means bitwise complement of 11. So you know that complement of 11. 11 value is 0, 0, 0, 4 zeros and 1, 0, 1, 1. This is the equivalent of 11. Now it converts this format into zeros into ones and ones into zeros. 1, 1, 1, 1, 0, 0, 0. So this is the answer you are going to get. But its equivalent value is minus 12. So it is stored in the form of minus 12. That's why we are getting the answer minus 12. Now, how to check this answer? How minus 12 can be represented? Minus 12 is nothing but 2's complement. 2's complement of 12. First, convert 12 into binary. What is the binary equivalent of 12? 2 6 ja 12, 0. 2 3 ja 6, 0. 2 1 ja 1, 1. 2 0 1. So 1 1 0 0 is the equivalent of 12. So left side you write 4 zeros, right? This is the binary equivalent. Now it is given as 4 zeros, 0, 0, 0, double 1, double 0. Now this is 12. Now to get 2's complement, convert into 1's complement, convert all zeros into 1's, 1's into 0, 1, 1, 1, 1, 0, 0, 1, 1. This is 1's complement. For this you add 1. So we are performing addition. So 1 plus 1 becomes 0 and carry is 1. This is binary addition. 1 plus 1 is 0, carry is 1. How? 1 plus 1 is 2 actually. So we are dividing 2 with 2. 2 1 are 2. The remainder is 0. So here we are writing 0 here and we are getting carry here. 1 is the coefficient and 0 is the remainder. Now again 1 plus 1 0. Again the carry is 1. So we are getting 1 double 0 on left side 0 1 1 1 1. So this is the equivalent of 1's complement of 11. So just now we got 4 ones 0 1 double 0. Same value we are getting here 410100. So that's why it is giving the answer minus 12. This is about bitwise complement. With this we have completed the binary, so bitwise operators. So what are the bitwise operators we have seen? Bitwise AND, bitwise OR, and bitwise exclusive OR, bitwise left shift, bitwise right shift, and one's complement. So these are the bitwise operators. So we will see C programs to implement bitwise operators. So now let us see Visual Studio Code to write C program for implementing the logical operators. Into the code. Now we'll write the program for this. Program to implement logical operators. Hash include stdio.h int main opening brace. So to perform these logical operators, we need two operands. For that, I'm taking integer a comma b, right? Printf, enter any two numbers. Enter any two numbers. Next, you write scanf, percentage d, double quotes close, comma, ampersand a, ampersand b, semicolon. So after reading these two numbers, what you do is you perform logical AND, logical OR, and logical NOT operation. So directly I'm performing these operation in printf. Printf percentage d. So I'm writing /n to move the cursor to the next line. Comma. Here I'm using a is less than b, a is less than b, and performing logical AND operation. I'm using another condition. A not equals to b. A not equals to b. Now similarly you use other operators. Control C, Control V. Here you perform, you write logical OR operation. You can use any kind of operation. I'm using my own operands, conditions. Here you perform not operation. This is logical not. We'll see what is the output of this. So here last statement return 0. So this is logical and this is logical OR and this is logical not. Save it and you compile it. So in the bottom it is asking enter any two numbers. You give the number. Here you give the numbers. 5 is the A value and 6 is the B value. When you give 5, 6, it is giving 1, 1, 0. What is 1, 1, 0? You take 5 value. 5 is less than 6. Yes. the condition is true. That means 1. This part becomes 1. Next, A not equals to B, 5 not equals to 6. Yes, this is also true. 1, 1. 1 and 1, the result is 1. Now come to the second one, OR operation. A is less than B, 5 is less than B, 5 is less than 6. Yes. Or 6 is less than 5. No. Second condition is false, means 1 or 0. 1 or 0 means 1. So here we are getting 1. Now the last one operation is not. A value how much? 5. 5 not equals to 6. Yes, 1. But before 1 we have not. Not of 1 is 0. So this is the output, so which explains the usage of logical operators. After this logical operators, next we are moving to bitwise operators. That we will see. Now how to implement bitwise operators. Now you do one thing. Program to implement bitwise operators. Now same program I'm using with some modifications. I'm using C, enter any two numbers, read any two numbers, right? Now first I'm performing C equals to A and B. This is the bitwise and operation. C equals to A and B. Now you write printf percentage %d slash n double quotes close comma you print C. Bitwise and operation. Next, what do? You copy these two statements, Control C, Control V, Control V, Control V. Now you do some changes here. First one is bitwise and second one is bitwise OR, bitwise bitwise OR, bitwise exclusive OR. I'm typing bitwise exclusive OR. Okay, now after this, what I'm using is left to shift with the amount of shift is 2. Next, I'm using bitwise right shift I'm using like this, B right shift of 2. Okay, and finally Control V. Now you write bitwise complement of A and you print C. So in this program we are implementing bitwise operators. First one is this is bitwise and this is bitwise OR, bitwise exclusive OR. This is left shift and right shift, bitwise right shift and bitwise ones complement. We will check whether there are any errors. Go and run it. Some errors are there. Okay, that we will check. Bitwise or operation. So this is not a correct operation now. Okay, I'm writing this. Control S. Now run it. So at the bottom it is asking any two numbers. So in the previous example we have seen A value 10 and B value is 11. No, A value is 11 and B value is 10. So same input I'm giving, A value 11 and B value is 10. We'll check whether we are getting the correct output or not. You see this. I have given 11 and 10. We got first bitwise AND value is 10, bitwise OR is 11, exclusive OR is 1, and left shift operation is 44, right shift operation is 2, and we got ones complement is minus 12. Same example we have seen, and same output also we have got here. So this is the program which is used to implement the bitwise operators. So with this we have completed examples as well as theoretical part of the bitwise operators, relational operators, and also logical operators. In tomorrow class, we will see more programs for implementing assignment operator as well as increment and decrement operators. With this, I am going to close the session. Thank you very much for watching.